I think by now it is established that GPU accelerated computing is part of supercomputing, here to stay, and leadership, and part of what we call leadership computing, at least in the Oak Ridge terminology where I come from. I would like to start by just reviewing some of the highlights. I think supercomputing with GPUs, you can say it started with Tsubame at Tokyo Institute of Technology in 2008. This was the first system that appeared on the top 500 list. But it was not really a supercomputer at the time. I had, around that time, that's 9 years ago, just before I started working at CSCS, on my new job at ETH Zurich, I had dinner with Steve Scott and tried to convince him we should go in this direction. He gave me a long list of reasons why this is not going to work. And then it turns out in the spring of 2009, he learned from his buddy Bill Daly that NVIDIA would introduce error-correcting memory and double precision, and those were two of the main reasons why you couldn't build a supercomputer with GPUs at the time. But this was fixed, as I said, and with the Fermi, and I think the first system was Tianhe 1A that actually led the top 500 list in 2010, I believe. And of course, Tsubame then very quickly also upgraded, or Tokyo Tech upgraded Tsubame. And of course, the big project that came in the US was Titan. That was then in 2012, I believe, the leader of the top 500 list. And it was, it remained, one of the leading systems up to now. So for a very, very long period of time. And actually, the cabinets, the Cray Xe7, that we had the first ones that were operational at CSCS in summer 2012, so just before Titan. And those were test systems because we were co-designing between a couple of applications and Cray. We were designing this system, Piz Daint, which in 2013 became the most performance system in Europe, and has been the leading system in Europe since then. And we had upgraded Pitstain last fall in November 2016, and so this was part of the process of bringing it up to date. And today it is one of the leading systems, you can say, outside of China. China is somehow setting a different performance metric. Of course, Tokyo Institute of Technology has been also developing and introducing the Pascal processors. And we are all waiting for Summit, which probably will start is being installed now, may show up on the top 500 list in November. I'm pretty sure they are trying everything to get the US back into the top 3. But the system really operational will be sometime next year, spring or maybe in the fall. So, this system will remain among the top operational systems, at least for a while. So far, we talked mostly about HPC, supercomputing. Saturn V, I think, is a representative of a new kind of computing, deep learning. And one that is actually a much smaller system that nobody notices because if you look at the top 10 or top 50 or top 100, but it's actually, I would argue, one of the more important ones. It was in 2015 when we deployed a GPU-filled system for operational weather forecasting. And so it was, GPUs are not a stunt at that point. There is a clear economic reason why we went this route. And I want to quickly explain what was behind it. So it was not demonstrate that it's possible to use GPU operationally for weather forecasting, but it was to solve a problem. And the problem was Meteo Suisse was upgrading, that's our meteorological service in Switzerland, was upgrading their model, going from a 2 kilometer to a 1 kilometer grid resolution, going introducing ensembles for their previous 2-kilometer resolution and improving their data assimilation. And if you add this together, this would be a factor 40 increase in performance that they required for the simulation performance, and they had a constant budget, both capital and operational, okay? And the whole thing had to happen between 2012, when we introduced their last system for their previous model, and 2015, when we had to go operational, so that they could go operational with the model in 2016. And in 3 years, you're not getting a factor 40 if you want to keep the footprint of the system the same. And so we were confronted with the problem in 2013, right the time when we were completing the co-design of Piz Daint. And one of the applications we had in our portfolio was Cosmo, was this climate model. And we had worked already for 2 or 3 years on refactoring this code. So this is a typical weather climate code, big monolith written in Fortran, very well engineered, very well performing, but hard to adapt to novel architectures. And we had rewritten some of the performance critical parts, and in such a way that we could have more modular and with proper composability and so on, libraries, and then architecture-specific backend. So we could support x86 and GPUs, and today also Xeon Phi with this system. And this was the basis then to design the system that was most appropriate to solve the problem, and that turned out to be this GPU-based system, Piz Daint, and I think was quite important for NVIDIA at the time from to make this point along the line of supercomputing with GPUs. And now what I'm going to discuss here is very briefly look at, where is this factor 40 coming from? Because we now have a software system that we can run on both GPUs, CPUs, on different architectures, and compare it to the old system, the current implementation that Deutscher Wetterdienst and many weather services are still using. So almost a factor 2 of this factor 40 comes from just rewriting the software. Sometimes you get a factor 10 or 100 if you start from a poorly written code, but that's not the case in Cosmo. So this is just running the same code on the same x86 architecture, the new and the old version. Then, of course, when we refactor, we have room for mathematical improvement. We have not fundamentally changed algorithms here, but still at the more fine-grained level, you have room to improve there, and that turned out to be a factor 3. And then the change in architecture from a x86 to a GPU was a factor 2. And so the rest is what Moore's law and architectural improvement will give you on the x86, and then we had to add a few more sockets. But there was no energy penalty because the GPUs were so much more energy efficient than the x86 that in the end we actually reduced the power and the cost of the power in the operational cost, and this pays for a person who is maintaining the new software stack that we had to build. So the message is there is no silver bullet. There is not one thing you can work on. But the other message is there is a factor 10, from refactoring the software and changing architecture on top of what you would get from just the normal Moore's law development. So it is well worth doing. And today we have 2 implementations of Cosmo. We have the standard one, and we have the new one that was very much motivated by this GPU-based developments. And there is a factor 10, as I said, between the 2 baselines. So as we move forward, we have to really be careful when we talk about 50 times improving the performance, you know, what are we starting off from, okay? But the system I will talk about most now is Piz Daint. It's this machine. There's a lot of numbers here. This is a fact sheet that you can download from this publication here, our website. It's the main point. It has roughly 5,000 GPU accelerated nodes with Pascal GPUs and Intel Haswell hosts. It has another about 1,400 dual socket Broadwell nodes, and all these nodes are integrated in one Dragonfly or one network with the Dragonfly and the Aries technology. And it has a peak performance around 25 petaflops on the GPU side and almost 2 petaflops on the purely multi-core side. Now, after this brief introduction and review of GPU-based supercomputing, I will talk about some of the applications that run on Piz Daint, and this is just a small excerpt I'm giving there. I would like to talk about science-driven exascale computing. That will be a good part of the talk. And at the end, I would like also to challenge the HPC operations, saying, you know, that we need to go towards service orientation of architectures as we move forward to be really useful. So one of the highlights that has been actually running before the upgrade, so still on the K20X, was this trillion particle n-body simulation in astrophysics. What they are trying to do here is this is part of a big project, a Euclid Mission, satellite mission that will go in 2020 to try to map out the entire universe that can be seen with you know, state-of-the-art instruments. And this is one of the main goals is so it's like a Hubble telescope, but absolutely on steroids. And it's using a combination now of big data, data analytics, and what this project did is, based on a simulation, generate a mock-up data set that they can now use to develop the data analysis in the next 3 or 4 years. So to be ready when the satellite is launched in 2020. And this was really a production simulation using the entire Piz Daint. We were really struggling at the time to keep everything up at this scale, because it had a time, I think in October, they had to deliver the data for the whole project to stay on time. Another example is this imaging the Earth, and this is happening on Piz Daint, but also in a number of other places like Oak Ridge. What they are doing here is they use earthquakes that they measure, simulate based on some model assumption of the Earth mantle, compared to the measured experiments, and then improve the model iteratively, so solving an adjoint problem. And it's basically doing tomography with earthquakes. And this is a community, a worldwide effort. So you can see here Piz Daint is just one of the stars there. There is a group, I believe, in Munich here working, so a number of groups working together, trying to get a better model for of the Earth mantle. And I'm very impressed to see the progress this community has made in the last 8 or 9 years since I've been in this job. This is a simulation from Peter Vincent on simulating, so CFD simulation of aircraft engine. It was one of the finalists of the Gordon Bell competition last year, again running on the full scale on Piz Daint and on the full scale also of Titan. And the remarkable thing here is not just the performance and the scalability, but is the software framework they have Okay, so they have PyFR is for the user is a Python framework. Then with architecture-specific backends, so C and CUDA in the case of if you have GPUs like on Pitstain. And I was very pleased to see this. Some of you have heard previous talks from me that I've been advocating this, and also in our own climate projects, that's what we are doing, pushing towards. It's good to see there are really users who do this, and this works at scale with the best performance. And I will come back later, I think the Gordon Bell Committee made some select decisions last year that they will end up regretting in history. But this was at least one of the finalists. Now I switch to science-driven exascale. I will still continue to talk about applications on Piz Daint, but I want to take this picture of, when we go to exascale in the future, what are we doing? One thing is clear, that exascale systems will be in the range of tens of megawatts of power. Okay, the petascale systems are somewhere between 5 and 10, maybe around 10 megawatts. Piz Daint is around 2.5 megawatts. We got a lot of credit for that because you have to imagine a megawatt running over a year is about €1 million or Swiss francs or dollars. And so if your power bill is in the tens of millions, just the power bill, that's you have to start thinking what you're doing with these systems. And this is actually one of the things you see also from these Chinese systems, the big ones, is they are struggling to finance the operation of these systems because they use so much power. And so basically what you have to take out of this is, when you build systems at that scale, that have that level of operational cost, you better know what you're doing with them. It's not good to build a system for some stunt and then shoehorn applications to make it somehow look good. It's not economical. And I don't think anybody can afford to just spend tens of millions on power they don't have to. And so this is why we are saying we need to pick the exascale problems very deliberately. They need to represent science problems that are clearly formulated and worth solving economically. If you invest hundreds of millions or billions in there, the value they represent have to have some macroeconomical value that's bigger than what you're investing. And then, of course, you need to go and solve those problems and not build a machine with exaflop and then try to show that you can also be relevant to those problems. And so one area that, and I've been on the record now for several times in the context of this EuroHPC discussion, is one area that I think needs to be looked at from a European perspective is weather and climate. And the reason is, if you go into this exascale race, you want to do it in an area where you're in the lead. Because we don't have much time. And one area that is clearly, you just look at the recent hurricane season and then at the US press and, the things that we know now for several years since Sandy and I think even Katrina, that the forecast reliability of this European Center for Mid-Range Weather Forecasting is much, much better than anybody else, okay? And so this is a recognized leadership that we have in Europe, but it is also clear that we are far away from the accuracy and the reliability that we need. So we need to look at this and what we need to do to improve. And it turns out there is a good match between what we need to do and ambitions for exascale computing that I would like to talk about. This is a simulation by Pierluigi Vidale, actually a PRACE project, where he was looking at, these are, again, these storm tracks from different simulations, different resolutions. So these are the lateral resolutions in the in these global climate simulations compared to observation. And what you can clearly see, as you improve the resolution, you see better agreement with observation. It turns out, and here now I have to reference to my colleagues, Björn Stevens and Tim Palmer, who, I'm not a climate scientist or meteorologist, but you just have to believe them that if we are pushing the resolution towards kilometer or potentially maybe even sub-kilometer scale, we are really making a leap that is a non-incremental step. So going from a few hundred kilometers resolution that they had back in the 60s to 10 kilometers is incremental. Going from the 10 kilometers to 1 kilometer or sub-kilometer, that scale is a non-incremental or is a big step forward. And the reason has to do with the way the models are parameterized. So there are some very unreliable parameterizations around convective clouds and these large eddies or ocean eddies. And they basically are unnecessary if you go to this high resolution. And so the model becomes simpler and more reliable. And I think it's that reliability that could really change the game in pushing weather forecasting from mid-range towards seasonal and in improving these more long-term, even decadal studies of climate development. And it turns out, as I will now show, that this, I think, is an exascale problem that we should focus on as a community. But it's not just the resolution that we have to worry about, and this is very important. And again, when you go to this example of Hurricane Irma, it's the need to do not one simulation, but you have to do many. So you have to run an ensemble. One example is when you do this forecast, so you see the four-day forecast, and you see this spread of potential trajectories that then only at some point later then was reduced to, and if you just focus on one hero simulation to look good at supercomputing, that is still not useful. Okay, so we need to increase the resolution, and we need to make sure the footprint of the calculation is such that we can run an ensemble. Okay, now what does this mean for performance? So I need to quickly talk about what is the metric that we are looking for. So there is, in HPL, there is a close link between the work that you have to do and flops. And that's why you can just measure flops and then you know how good you are in solving the problem. That's not the case here. Here what we need is we want to run a simulation for weather forecasting, say 10 days, 100 years for climate, and even thousands of years if you're spinning up a climate model, so doing the tuning of parameters. You want to run these 10-day simulations in a few hours. Otherwise, they are not useful. And that then gives you a ratio of 100. Or you can then compute simulated years per day, and then you get a number about 0.3. For a simulation to be useful for weather forecasting, or 3 for a simulation useful for climate. Okay, so remember these two numbers. I will keep repeating them. Okay, so now what we are doing is we take this implementation of the Cosmo model that we know is, probably at the limits of what we can squeeze out of systems today, and we have Piz Daint available, so up to 5,300 GPUs, and we are going to run this. So this is not a climate simulation, but it's a representative of a climate simulation to get a feeling where we are with performance. So we run it on a so-called baroclinic instability problem for study for going from 80 plus to 80 minus degree, covering about 90% of the Earth's surface with Cosmo 5 on GPUs or on CPUs. So we can look at those two architectures. And so we run this. This is a standard test problem for climate codes. And then we get numbers. So we scale up to 4,800 GPUs. We could go to 5,300 now, but at the time we only had 26 cabinets upgraded. And then we get these numbers. For different resolutions, I will come back to this, we get a number of simulated years per day of what we can accomplish. And the point here is, it turns out when we look at the performance we get, okay, and then we compare it to other models or other implementations, including the implementation of this stunt they did on the Sunray system in Wuxi for the last year's Gordon Bell Prize, we see that we are, comparable, or in the case of that problem, we are about a factor 2 or 3 faster. So that's why I would say these are the numbers that are, and why is it? It turns out that in that paper, they have chosen, chosen a time step that was too big, that violated certain mathematical properties that you have to have. So they were basically, the solution was mathematically wrong. But then you can go back and you can estimate, what would have their performance have been if you adjust the error they have made. And so in this paper that we have written, it's available here, you can go into the details, how we get to this estimate. Okay, so this, I would argue, is now the baseline where we are running on one of the biggest supercomputers and running probably one of the best implementations that we have on these systems. And you can see we are, the 1 kilometer resolution, we are at 0.04 simulated years per day, which is for climate a factor 100 away in performance. So we can scale to the right problem, but we are a factor 100 too slow. Now you can go into details, and I don't want to spend too much time on this, but you can go into details and you can study, you can look at these points here, and you can see this is actually quite a good weak scaling that we have. And you will see here that we still have a factor 4 or 5 if we had more nodes, or if we could put more threads on a GPU. So of this factor 100, a factor 2 will come just because using Cosmo is not the efficient grid to use. We have better implementations of grids like these icosahedral meshes, and this will bring the performance up a factor 2 immediately. It's non-trivial because these are block-structured meshes that are more difficult to handle from an implementation point of view, but we know it is possible. And then we have another roughly factor 5 that I think we can get from further weak scaling, but then we are still a factor 10 away. And for that, we really have to now go into detail and to a real co-design effort how we are going to address this and get this out in the coming years. And that's just to get the time to solution right. Okay, having, I said, one simulation running on a system with tens of thousands of nodes is not what we need. We need at least to reduce the footprint of the simulation by a factor 10. And I think that's the challenge that I say this is an exascale challenge. And if we haven't solved this, even if we have a machine that does an exaflop, it is not a solved problem. We have to solve this problem. And we will have data problems that are associated with this. So, and that may actually be even the bigger problem than just the performance problem. Because if you take the CMIP, kind of data that they produce today, 2 petabytes, and you're running, and I think they run, I don't know, around 50 to 100 kilometers. If you develop the technology that they can do ensemble at 1 kilometer resolution, but you don't change the workflow, you will create a factor 10,000, 5 to 10,000 more in data. And if you, so don't change that, you go from 2 petaflop to 50 exaflop just like that. And so it will require also looking at the workflow and how we do things in these climate simulations. And so those are the problems we need to work on. And I've given you, this is clearly the one problem at CSCS and ETH that we're looking at very closely. There are other problems like material science, electronic structure, or molecular biophysics, or I said also geophysics. One of the main points I would like to make here is it has to be the community that defines the problem that you have to solve. And I will also argue very strongly, and I know there are some people who don't like this argument, also some of my colleagues in PRACE and other directors of computer centers, it has to be the science communities that lead the effort. And so this is a statement I'm making to the computing guys. You know, it's, we enable this, but the intellectual leadership has to come from the communities. But it's also a message to the community that you need to work on those problems, get behind them, organize behind them, use your organizations like ECMWF in the case of weather and climate, or for material science and molecular simulations, we have SECAM. Those are organizations that have been around for decades now and that the communities are organized. So we need to put these at the helm and make sure they are engaged. And I'm sure for seismology, I don't know the details there, but I would very much like to see that as an effort, and I'm sure there are some more problems that we can come up with. Okay. Good, so that's what I have to say about Exascale, and we can definitely, you know, I'm happy to answer more questions. I know I'm stirring the pot here, but I think we need to. There's also this thing about communities engaging. Imagine you had, you know, some organization that just knows how to build big accelerators and also big computers. And they now say, we are going to solve all the problems of the high energy physics community, and they are not talking to CERN about it, okay? It would make no sense. Okay? But this is, in a sense, what we are doing sometimes in supercomputing. We have these centers that know how to build big systems, but they are not, you know, they don't really understand the problems that need to be solved. And I think we need to change that. So I want to switch now and make a short detour because Piz Daint has a lot of GPUs, so it gets some attention in the deep learning and machine learning community. And so I will use that to move to my last topic, which is really that we need to restructure how we do operations in computing, in high-performance computing, and move towards this service orientation. So something we always get asked to is, you know, how do your machine learning packages work on the system? And the experience is, actually, this is not very challenging. If you have, you can take almost any machine learning package, and they are like applications, and we're used to moving applications onto supercomputers. And so the surprise is not big that we can pretty much support all packages. And when I say some of the support is in progress, what I mean is CSCS has people on the more future systems, or some of the scientists who will support these, but our general support organization is basically focusing on those where we have users. So in progress means as soon as we have users, we can change from in progress to yes at this point. And I may not even be totally up to date on this list here. Now, why would you want to use a machine like Piz Daint or nodes on Pitstain to do deep learning? This is an example using TensorFlow on some standard tests. Well, if you move from your workstation to a node on the multi-core side, or then even on the GPU accelerated side, you can typically get this factor, in this case, factor 20 speed up. And this is not a surprise. This is just because the matrix multiplications in your training are just so much faster on the Pascal GPU. And that's also, to a certain extent, what they are built for. So you get benefit if you want to solve your problems faster. Of course, we're talking about the supercomputer, so people will always ask about scale, and this was one of the news also out in December 2016 where there was a project from Microsoft and Cray working together on the Piz Daint system to scale CNTK. And they showed some numbers, and there's a lot of other work now happening, even supercomputing papers coming out in this. And they will all see, yeah, you can scale, and at the time to a few hundred GPU, strong scaling, or weak scaling. Weak scaling is always easy, okay? So you can tune things, and you can weak scale, and you can make your mini batches ridiculously large, okay? And to a supercomputing person, it looks scales, okay? Now, whether there is a problem that can make useful use of this type of simulation is not clear to me. And that's another one of these examples why in HPC sometimes we really have to listen to the community first before we try to do something. You know, or yeah. And actually the main problem we have here, I believe, is that the underlying algorithm, stochastic gradient descent, doesn't scale. So what are they doing? They have these training samples that they put randomly into these mini batches, and then you take a mini batch and you distribute the mini batch over different MPI ranks. And then you update the gradient, and then the new gradients are summed over in an MPI all reduced, and then the weights are updated on every one of the nodes, and then you iterate back. Now, the problem of this is really the only parallel or scalable section of your algorithm. We know we run into bottlenecks here, but even this part is not scalable. It's well distributed, the work, but so we run into Amdahl's law problems in this. And so the real work should be to work on the algorithms. Of course, you can first try to make a better implementation of this part. And that's essentially what is typically done in this HPC work so far. But it's not, but we really need work on the algorithms. And then you need to talk to the machine learning experts, or those who understand the mathematics, okay? And so we had Thorsten Höfler and I went to one of our colleagues at ETH, who is very well known. And his answer was basically, we develop algorithms, we don't have time to deal with C++ or C or MPI. And Thorsten was a bit upset because, you know, that's like you're not developing algorithms, but of course, which of course he does too. But this is a message that that basically the message is we need to make these systems more productive. Okay, you know that OpenMP or Fortran or OpenACC doesn't even show up in this statement. Okay, so we have to change the productivity, and I think we hear this from a lot of scientists, including scientists who use HPC systems. And I've shown you Peter Vincent's work, you know, using Python, but this allows you to develop, you know, even what we need is we need to support Jupyter and interactive notebooks on these systems. Another thing we have to do is we have to support Docker containers for the deployment of the software. And here I mean not containers for the sake of using containers. No, I mean Docker, because that's what the community and the world out there is using. And Docker has some drawbacks on HPC systems to do with, if you want to use the parallel file system, you have some security problems you run into. But you know, some of our colleagues at Berkeley, so Doug Jacobson and Shane Cannon, they introduced this shifter architecture that you can then run your Docker on top of. And that solves pretty much these issues. So you can securely run Docker on an HPC system using shifter technology. And we are collaborating with them and also NVIDIA to make, in the meantime, we can expose the GPUs of Piz Daint to Docker containers, so everything is working. And today we actually, in the Human Brain project, which we also serve, we have a service for supporting Docker on these machines. And this, of course, is available to other environments as well. Now, so given that we can support Jupyter, we have even a project, and Dirk Pleiter is in the room, who was one of the masterminds behind it, along with Sadaf Alam, on interactive supercomputing, and so on. We have everything basically technically lined up, okay? But this is still not enough, and this is now my last point that I want to make. It has to do with our usage model. So this is essentially how supercomputers are used anywhere around the world. You have a user on behalf of the community or from the community logging into some nodes and using the scalable machine behind it. And you can see from this, supercomputers are Unix workstations, in a sense, just big ones. That's what they are today with a POSIX file system and so on. And, but this is not good if you have to, like, we have a project called Materials Cloud that is trying to make simulations, workflows, and not trying, actually it's a serious multi-year project, making simulations, workflow, and databases available to a community through web interfaces. Another example is the Human Brain Project Collaboratory that has very similar setup. And those are the two projects we've been working with to try to shoehorn our architecture into this web-based, accessible system, for the Human Brain Collaboratory, HBP Collaboratory, or the Material Science, the Materials Cloud platform. And it worked. The problem is it's a lot of work on the side of the computer center, so it's not scalable. If I cannot support 50 of these platforms, I would have to hire about 100 people to do this, and so that's the part that doesn't scale. I don't have enough office space in Lugano. I probably have enough compute room space, but not enough office space. So we need a different solution, and the solution is quite obvious. We need to organize our infrastructure behind, so whether it's OpenStack clusters or our HPC systems or the various storage systems, we need to organize this behind a web-accessible set of infrastructure services, so we need web-based APIs to work for this. And this turns out to be possible. So again, the technical thing to develop these web APIs, it's tough. You have problems like you want some of the storage models, they don't fit onto the POSIX file system. So you have to work on those things, but those are all technically solvable problems. It's more an organizational issue, how we organize the computer centers to make this work. And then you want once you can run services like this, you realize that the HPC centers have a very good feature, namely they are on top of their typically on top of their software stack and the systems because they do frequent maintenance, site-wide maintenance or system-wide maintenance. But then you cannot reach the high availability level unless you have double redundancy in everything, which doubles your cost for everything. So a service needs to be accessible, particularly if it's used through the web, but it's hard to make this accessible availability possible in a computer center, HPC center. And so the way to solve that problem is to collaborate between different centers and federate the service over not 200 data centers like the grid. That's not what I'm talking about. I'm talking about federating over 2 or 3 or maybe 5 sites, and that can agree on the service, not the implementation. The implementation should be site-specific, but agree on the service, and then on the resources they allocate to this federation. And in principle, you need, for a given service, you need 3, and you reach incredible availability, because if you have 3 supercomputer centers, coordinate their maintenance, if you take the maintenance downtime away, the reliability of these centers goes up to 99 or above %, and now you have 1 does maintenance, you have 2 with this 99 and above reliability, you square that, you get to very, very high availability of the service. And we actually have a collaboration. It started between CSCS, Jülich, and Cineca. So these are, I would say, the 3 first ones. In the context of the Human Brain Project, we have been adding Ceuta and Barcelona, so we have 5 sites. As I said before, we don't need hundreds of sites, but I'm sure we will be adding in a few years some more. There is certainly CSE in Finland, that's one of the pioneering places, or Surf-Sara in the Netherlands, that are pioneering places in the whole area of data and data-centric computing. So I think this is one of the important directions we have to go from an HPC point of view. But one thing we have to realize, we're not inventing anything new here. It turns out in this service orientation of architectures, there is even an ISO standard. So the IT industry has been working on this and somehow has been ignored by at least the grid computing community. I haven't seen anything discussed like that there. And certainly ignored by the HPC community. So it's not something new, but something we need to make sure we adopt and make the appropriate organizational changes. And this is a last slide before I come to summarize. Once you go into the service orientation, very interesting things start to happen. So we have this aim to separate infrastructure with a web service layer, web API, web accessible API. Then we have platforms, and then we have an API and a platform service, and then we have software running on top, application software. The interesting thing is, so there are 2 things on this diagram that are fundamentally different from how we would run CSCS a year or 2 ago. One of them is we have external platforms like this Materials Cloud or the Human Brain Collaboratory running on top of our infrastructure. So we expose the infrastructure to external platforms. This is possible today. The other thing is that traditional HPC needs to transition from an HPC, a Fortran code running on bare metal, into codes like CP2K, which is still a Fortran code, but not always running on bare metal. It's running on top of an infrastructure that is called, we call it an HPC platform. And so you can run CP2K as a service on top of this HPC platform and on Piz Daint. And so really we are talking about transitioning our software stack into a platform service that can run on a number of infrastructures and combine this then with Jupyter and the Docker, the deployment mechanisms. And then you suddenly see that the data science apps and the HPC apps, they start looking very, very similar. Mathematically, they are fundamentally different. They need other backends and so on. But from a usage point of view and productivity point of view, they become very similar. And I think this is the way to go to make progress. So to summarize, I gave you some of the highlights in supercomputing over the last 9 years, starting with Tsubame and work at Tokyo Tech and Oak Ridge and CSCS. So these are the 3 sites that do supercomputing based on GPUs at large scale around the world, or are leading this. CSCS is, and Piz Daint is Europe's window into this exciting development. I've shown that GPU-based systems are even important for and can be used for operational forecasting. Then we looked at a number of applications, and I would like to highlight this work, this Python-based work at scale. And so Piz Daint is really operational for many application domains. We discussed a long time this science-driven exascale computing, and my main point there, takeaway is, and this is really the message to the science domain, is they need to start taking charge of these problems, of these exascale problems, and organize behind them and take the lead. And finally, I believe that setups like CSCS or Jülich or the large HPC centers in Europe, they need to transition towards a service orientation of their architecture. And one important message, don't try to invent new programming models in a few years. Okay, that's something that takes decades. There's a few models, new models that evolve. They take huge investments like CUDA, and so you're not with some government program just going to create a new one, and certainly not with some of the programs the way we run them in Europe. It's important that we adopt what is out there and that the industry is developing. And so C++, C on one side and Python on the other side, I think that's fortunate for us because they are useful to HPC, and there is a huge momentum and investment behind these environments. Thank you.